Today you will be able to solve systems of linear equations using equality. Systems of linear equations might at first sound kind of overwhelming and the notation might look kind of scary, but all a system of equations is a set of numbers or a set of equations that you deal with all together at one time. Not all systems are linear, but the ones that we are going to be working with and the ones that we are going to be solving are all linear. Let's refresh our brain a little bit about the types of linear equations. First, we have y equals mx plus b. This is slope-intercept form, and this is what we are most familiar with. M is our slope, and b is our y-intercept. We also have standard form, ax plus by equals c, where a, b, and c are all integers. Let's start with what we know about the equation y equals 3x minus 5. First of all, on a graph, it looks like this. We can say that a solution to this equation is 2, 1. This point right here would be a solution to the equation because this coordinate point lies on the line of y equals 3x minus 5. I can prove that this point is a solution because when I take the coordinate pair 2, 1, I'm going to plug in 2 for my value of x and find that it equals 1. Therefore, my x is 2, my y is 1, hence my coordinate pair of 2, 1. Any other coordinate point that lies on this line would also be considered a solution to this equation. Let's consider a system of two linear equations. In other words, this is a set of two linear equations. Before we do anything, I'm going to show you how this will be notated from now on. It will go from being written as two separate equations to two equations written just like this. A solution in a single equation is any point that lies on the line. So in a system, it's the one point that lies on both lines. In other words, it's the point of intersection. So before we look at solving this symbolically, we're going to look at this on a graph. Graphed on the same coordinate grid, you will see that these two lines intersect at this point right here. So I can see that that would be my point of intersection. In other words, that would be the point of equality when I've set this linear system of equations together. The solution to this set of equations is 2, 4, and I'm going to prove it to you, showing you symbolically. Because they are both set equal to y, I can then set them equal to each other. So 3x minus 2 equals negative x plus 6. I've added positive 2 to both sides to get rid of the negative 2 on the left. So far I have 3x equals negative x plus 8. I then add positive x to the right and the left, leaving me with 4x equals 8. Divide through by 4, and my value of x is 2. I'm not done there. Now that I have my x value, I'm going to then plug it into one of the two equations. It doesn't matter which one. I'm going to plug that x value into one of the equations to find the y value of the coordinate pair. Plugging in 2 for x leaves me with a y value of 4. I plugged it into the equation y equals negative x plus 6. It didn't matter which equation I chose, but that's just the one that I did. And now that my x value is 2, my y value is 4, I have just proven that point of intersection symbolically is 2, 4. This is what we would call the solution to this system of linear equations. This next example comes from page 53 in your textbook. Let me set up the equation for you, the problem for you, and then I'd like you to go ahead and solve this with me. Here we have a table of equations for the flight patterns at the... Whoa, I did not read that correctly. Okay, here on the right side, we have a table of equations for the flight paths at the right. To find the intersection of WC19 and AA29, you need to find the xy pair, the coordinate pair, that satisfies the system of linear equations below. The bracket is a special notation used to indicate a system of equations. Here we have an example where Jeff left, the person in the story, writes the following to solve a system of equation. Uses their two equations and sets them equal to each other. Hence, systems of equations through equality. They are set equal to each other. So you can see his steps along the way. He added the 1.5x to both sides. So on the left, he was left with negative 1 and 2/10 x equaling 1 and 6/10 because he added the 2 on the left side to both the left and the right. He divides through by negative 1 and 2/10 and ends up with an x value of negative 4/3. So this value right here does not mean that we are done. This value right here simply gives us the x value in the solution of the coordinate pair. What we want to find now is we want to find the y-coordinate for the point of intersection. Setting two equations equal to each other is not a new concept for us, so this is actually review. So let's do this. Let's take that first equation, y equals 3/10 x minus 2, and we're going to plug in the value of x for x, which is negative 4/3. Now it's just a matter of simply calculating the value of y. The value of y is negative 8/10. So my solution is negative 4/3, negative 8/10. So in the context of this problem, the flight AA29 and the flight WC19 would intersect, their flight paths would intersect at the point negative 4/3, negative 8/10 if you were to graph their paths on a coordinate grid. I would like to try one more example. You're going to notice that in this example, my two linear equations are written in two different forms. What if my first equation was written in standard form? What would I do? I am always going to want to take my equations and put them in slope-intercept form, in y equals mx plus b. Then I can solve away because they're both going to be set equal to y equals mx plus b. In fact, I'm noticing they're both in standard form. So let's take a minute and convert these into slope-intercept form. 3x minus y equals 30 now becomes y equals 3x minus 30. X plus y equals 14 now becomes y equals negative x plus 14. I'm going to rewrite my new system of equations to look like this. And now I'm ready to solve because they're both in slope-intercept form and they're both set equal to y. I'd like you to pause the video at this time for you to do this yourself and then check your work with mine as we're going along. So please pause this, try it on your own, and then once you have your answer, unpause it and check to see that your work and answer match mine. You can see my value of x ends up being 11. I plug 11 into the second equation and I get the y value of negative 3. Therefore, my solution to this system of linear equations is 11, negative 3. A couple tips to remember as you go on to solving this on your own. First, start by putting both equations in slope-intercept form if they are not already in this form. Also, after you solve for the x value, do not stop. Continue, solve for y by plugging x in the equation. There you go. You have just successfully solved a system of linear.
Made with Doodlecast Pro.